Hi. How are you guys holding up? It's been a long day, I'm sure. So my name is Rahul Padil. I'm a lead program manager on the PPL and the concurrency runtime team. So you've been hearing about async all day. Windows 8 is promoting async pretty heavily in order to build fast and responsive applications. So I'm here today to talk about how to do async programming from C++. And you'll see how simple and powerful we've made this for you. So before I get rolling, I just want to do a couple of audience questions. So one is, how many of you have already built a C++ Metro app already? About half the room. So I assume you must have used async already, right? How many of you have heard of PPL before, the Parallel Patterns Library? Wow, that's more than the async. OK, that's great. So PPL stands for Parallel Patterns Library, which we actually offer writing code against 3 parallel patterns. So one is the data parallel, which is parallel for each, parallel sort, reduce, transform, and all the good stuff. The second pattern is data flow, where you can string a bunch of message blocks and exploit concurrency that way. And the third one is tasks, continuations, and async. And that is the focus of today's talk. Okay? So I'll spend a couple of slides just getting a good mental model of the async. And that'll help us ground the conversation for the rest of the talk. And then we'll quickly dive deep into the C++ constructs for async. Okay? So on the UI thread, the paradigm is pretty clear. So if you block, you break. You break the user's expectation. Whether you block or whether you do long-running operations, it's the same thing. Users get frustrated. So take a very naive example. User is asking, I want to fetch an image from the network, process it, and then I just want to see it on my screen. Now, as an implementer, as a developer, if you made this synchronous, no matter how fancy you make the icons look, users always get frustrated. You get the busy signal, I'm thinking signal. Users get frustrated. And when users get frustrated, they leave your app, and they go to Facebook to become happy again. So I'm afraid to ask how many of you are on Facebook right now, but I don't want to know the answer. So moving on to async. So the async thing is essentially the UI thread. All it does is just set up the structure to say, look, go get this image from the network, process it, and then update the UI control when you're ready, but just not on my thread. So specifically, I'm going to say, go do the fetching and the processing on some other thread, but I need to do the update of the UI control on the UI thread. Right? The update of the UI control, that box, they will be sharing some. They'll have some shared objects, some control. So it's important for the UI thread and only the UI thread to be able to update the UI. Okay? The advantages are simple. The app stays responsive to multiple requests. You can run concurrently, and you can take advantage of multiple CPUs. And operations can be canceled anytime. So if the user says, I'm no longer interested in this operation, I want the ability to be able to say cancel it. So now we'll go into the async concepts in VC++. Note that I put VC++. As Herb mentioned in the morning in the keynote, the std async and the promise only gets us about a third or half the way. And so we've really tried to support the whole thing with the tasks model. And so everything I talk about will be the task model. It won't be anything to do with the std async or std future. And as Herb mentioned, we're working very, very, very closely with the ISO committee to bring a model like this, hopefully with the then word itself, back into the standard. Okay? So first of all, PPL task. What is a task? A task is a unit of work that can run concurrently, that can be run somewhere outside of my thread. So all it takes is a lambda. Okay? In the lambda, all I'm doing is compute something like Fibonacci of 40, right? And it is templatized by the return type. So in this case, it's integer. And that's it. So just doing this will take the Lambda and put it off on another thread, preferably on the thread pool. In this case, it's powered all by concert. Now, the thing that today Async and Fuchsia doesn't have is this, which is the then. Once I've set up a task to go run somewhere else, I want the ability to say, once that task is done, come and execute this other thing. So once you're done with this, then go do something else. So then itself returns another task, and the Lambda that the then takes, the input parameter must match the return type of the previous task. So in this case, the task T is returning int, so which means which is matched with the input parameter of the Lambda. You could set up multiple continuations or multiple thens on the same task. So you have task T, and we've set up two tasks, T2 and T3. Both will get called, both will continue after T is done. Okay? And both T2 and T3 can run in parallel on different CPUs. Okay? You could also do a classic .get, like, I'm done processing this task, or I'm done, I need the result of this task before I can move on. I can do a T.get. But the disadvantage of T.get is it is a blocking call. So if the results are not computed yet, it will block. And it's optional. You don't have to call get. Now, you can build more complex graphs by chaining a whole bunch of thens together. So in this case, we call this a .then ladder. So you can actually have multiple asynchronous operations all chained together in this way. Okay? You could also go get a little bit more creative, and you start building continuation graphs, which is each of the subtasks start creating their own continuations. Now, this becomes important if you're saying async is everywhere, and async, every method that takes more than 50 milliseconds is going to be async. And so essentially what you're going to have is an async operation calling another async operation, calling another async operation, and pretty soon you'll have a complex graph to manage. Right? Now, sometimes you're interested in grouping these tasks together. So we have the constructs to join and do join and choice. So let's take an example. So I am going to, let's say as a user, I kick off, as a developer, I kick off like 4 or 5 tasks to go and search through files and get me the results. When all these tasks related to searching the files are done, then go and do a sort. Okay? So for me, those 4 or 5 tasks that I kicked off asynchronously are logical, and they can be grouped. When all of them are done, I want to do something with that. So we have a construct called when all. When all itself also returns another task, and you can do more continuations off of that, but that's secondary. So in this case, what we do is, so we have 3 tasks, T1, T2, T3. Each of them return a string. Okay? As soon as they find a file, they tell you which file it finds. And the when all takes a vector, so you can, and when all of T1, T2, and T3, when all of them are done, go and schedule another continuation on top of that. So in this case, in the then, I would put a sort, like, go sort it, and then present the results later on. So we've also made it convenient, especially if you just have 2 tasks or 3. You could also just use the AND operator, so you can do T1 and T2, and you'll get the .then. Now, we don't recommend using AND if you have like 10, 15, or 100 tasks, because each AND sets up its own continuation. You contrast that with when all, it only sets up one continuation for all the tasks. Okay? There's another construct called when any, which is when any of these 3 tasks are done, then go and schedule a continuation, which is we're interested in just the first result. So the user is searching for files, and you say, oh, the first time I find the file that's good enough for me, and I'm just going to go and execute a continuation off of that. Okay? So once you've created a lot of tasks, you can group them logically in your head, and you can do some advanced continuations on those. Okay? Now the big thing is error handling. So in the synchronous world, you're calling a method. If there's an error, you know exactly where you are, where you came from, where you're going to go next, and you know what to do with the error. In the asynchronous world, what we've done is we've taken the flow and we've said, this piece of code, go do it somewhere else. Okay? Now, we have to wonder, so what happens if there's an exception there? And what is the semantics? So what should my behavior be? What should happen to the task that depends on the value that that task was giving? Right? So error handling becomes interesting and becomes important. So let's take an example. So you can say, OK, let's keep it simple. Let's localize the exception handling. So wherever I'm executing a piece of code that could throw an exception, I could do a local try catch there. So in this example, I've shipped off task T to go do somewhere else. In there, I put a try catch. I'm expecting A to throw. I put a try catch, and I handle it. Now the big deal is, what is the semantics of continuation? Should I continue? If I do continue, what is the value that T should return? Like, should it return a dummy value? Should it return a null value? What should it return? And what should the continuation actually do with the value when the previous task has thrown an exception? So it doesn't quite align with what the developer was trying to express. And then if you so what we've introduced is something called task-based continuation. So it is a special continuation. So pay attention to the yellow box, which is the task int of tn. So it is a special form of continuation. So remember when we introduced task, we said the then takes a lambda, and the parameter of the lambda is the return value of the previous task. So in this case, the previous task is returning int. It's a task of int. Right? But we're saying that the then continuation is actually taking task of int, not just int. Okay? That is a special signal for PPL to say, oh, this is a special type of continuation, and we handle that slightly differently. So what we do here is if any task in the previous chain, in this case it's just one task, if that threw an exception, we take that exception, marshal it all the way to the first task-based continuation. So you have one place where you can handle all the exceptions. Okay? So this becomes more interesting when you have a more complex graph. So let's take a simple dot-then ladder. Okay? So the task T, the first one, that's where the exception gets thrown. Now, what we say is, OK, the developer really wanted not to continue the next one, not to continue the next one, go straight to where my exception handling is. And so the task-based exception, task-based continuation sort of becomes a finally block. Okay? So there you could do like t.get. Now remember, this t.get specifically here, the tn.get that you see in the code, is actually not blocking because we know that all the previous tasks are done. That's where this then is scheduled. So we know it's not blocking. Either the result is available, or we have the exception coming out of that. So that's error handling. So as you build more complex graph, this kind of paying attention to this will really, really help. Will help with your productivity long term. So the next thing we said what async should help with is cancellation, right? So user is fired of a task. It could be either for speculative execution, or like I'm genuinely not interested in the result anymore. So I want the ability to be able to cancel. So we have something called cancellation token source. Okay, so that is from the cancellation token source, I can generate what we call cancellation tokens. Okay. So cancellation tokens subscribe to cancellation token sources. So you can have n number of tokens. When constructing a task, we can pass the token as a parameter to the constructor. Okay? And the dot-then variation also accepts a token if needed. By default, it inherits the token. The dot-then inherits the token. And by specifying this, now anyone who has access to the cancellation token source, let's say in this case, the thread that actually set up the task, can say cancel, I'm no longer interested in the result. and we will cancel the task, and we'll cancel the task tree as well. Okay. Now, we only cancel the task. It's only safe to cancel the task if it has not started yet, or it's completed. I mean, in which case it's not cancellation. But it's only safe to cancel a task once it's completed. And so if, in this case, if task T has already started and it's really long running, we want to give the ability to the developer to be able to check if it has been canceled in anticipation that I'm running a really long while loop. So you could, we have a method called isTaskCancellationRequested, which will essentially look at, I'll look at my current token and I'll check if the token source has canceled. Okay. Now imagine this in a really complex graph of async operations that have been fired off. And if you're not interested in the result, all tasks that are subscribing to this token source will get canceled automatically. So we expect a lot of them to have not even have started, and so you'll actually save a lot by just canceling those off. Okay? And when you set up these continuation graphs, by default, we inherit the token. So whatever the parent, if the parent had subscribed to a particular token source, then all the children of that async, all the children of that continuation will get that token as well. So everything we looked at until now is all C++, no CX, and it's, of course, only VC++ right now. And it's available with Visual Studio 11. And it's available, you can use it for Windows 7, Windows 8, desktop, Metro, it doesn't matter. Okay? Now we'll talk about what Hattie was mentioning earlier, which is there is the Windows runtime async interfaces. Okay? And each language has chosen a way to project on top of these async interfaces. And the choice for C++ is PPL. It was a perfect fit. We'd already started that work. And it happens to be a perfect fit for the async interfaces on the Metro. So what does Windows Runtime give us? It gives us, so the first class that it gives us is the iAsync action. It's essentially an async operation that returns no value. Okay. You set the completed property. Completed property is equivalent of the then, which is where you schedule the continuation, but you can only do it once. You only set then once, and you can't have a chain of those. Okay. If you, there's also a class called iAsync operation, which returns a T result. So if you care about an iAsync operation that returns, you have the iAsync operation. And in the completed property actually takes a lambda. You can do .getResults to get the results of the previous task. Now you have the same, both these available with progress reporting. So if you have something, if you have a long-running operation and you want to give periodic updates to the UI, you would use the progress reporting. So in addition to the completed and the get results, you also have a property called the progress property, where you set another lambda to be called periodically. Okay? Not periodically, at the will of the underlying async. So now let's put it together. So we have the raw interfaces from Windows Runtime, and we've looked at the C++ tasks. Now let's put it together and see what code starts looking like. So this still doesn't have PPL, this code. So using C++ CX, but no PPL, if you call the raw interfaces, what you get is this. So get file async is an inbuilt operator for getting file. In fact, there is no blocking way to do it. And what that returns is an iAsync operation of storage file type. And I set the completed property. The completed property just takes another lambda, right? And I say, okay, once that file is, once I get the file, go do some work. Now let's look at the transformation with PPL. It's pretty straightforward, and it's lesser code too. All PPL does, what we've done is, we've added a method called createTask. So this is not in beta yet, but we have released it as a sample pack for the beta, but it will be in the next release. It will be in the coming final product. So createTask takes an iAsync operation and creates a PPL task out of it. Okay? And then you can schedule, instead of using the completed property, now you set thens, and you get the continuation. Now, what we've done with just these 2 lines of code is we've brought the entire power of PPL that we've looked at in the past, not in the past, 15 minutes ago, the cancellation, the error handling, the continuation, the complex graphs. We've brought all of that power to Metro, right? And the code is a little bit more concise. It's not obvious the sample is too small. The code is a little bit more compact. But as you write larger code, this code becomes nicer and nicer and cleaner. The next big thing is the fact that we're returning a task of string compared to the previous example where we were returning a read string. So if you want all methods, if you want to promote async heavily, and if we believe that with async you can write really fast and responsive apps, then don't you want your methods that you write also to be async, right? So instead of returning the actual string, we return the task of string. Now the caller can say t.get if he doesn't care about blocking or async, but it gives him the option, it gives the caller the option to schedule another continuation if he wants. So this read string task actually became another async operation of its own, right? So those are the 3 benefits. One is you get more concise code. Second is we bring the whole power of PPL to Metro. And the third is we encourage more asynchronous methods creation. Okay? So now let's talk about the execution context a little bit. So this is probably the most frequently asked question in the forums. So this is the same diagram that we saw on the second slide, where the UI thread is set up 3 boxes: the fetch an image, process image, and update the UI control. And the fetch, we said the fetch and the process must happen on a different thread, specifically not on the UI thread, because at that point I'm freezing the UI. But we're saying update the UI control back on the UI thread. So we need a mechanism in the continuation chain to express this intent. So it's pretty straightforward. So what we say, when you create a task, by default, it gets scheduled not on the UI thread. Okay? And for the process image, again, we said we don't want this to run on the UI thread. So we pass a parameter to then, which says task continuation context, use arbitrary. What this is essentially saying is to schedule this back on the MTA, COM MTA, which means that any thread is free to pick up any thread on the thread pool, in this case it will be the concert thread pool, is free to pick up this continuation to execute. Now the thing that we want specifically to run on the UI thread, we say task continuation context, use current. Because the UI thread is setting up the structure, and the UI thread is a ASTA, single-threaded apartment COM single-threaded apartment, this ends up scheduling it back on the UI thread. So when the UI thread actually has cycles, it will go and execute the then. Okay? This is also the default. So you don't have to specify task continuation context use current. It is the default for Metro. Okay? Now, both these highlighted APIs are only available for Metro. It makes sense. It only matters to Metro UI programming in this case. So, okay. Now, the next thing that's specific to Metro, again, is the create async. Harry, in the previous talk, walked us through some pieces of the code, but we'll talk about this, and we'll see a demo pretty soon. Let's say you have a library, you've written a library, and it's called synchronous process image, and we want to make this asynchronous. You want to call this from the UI thread. You want to make this asynchronous. So we have a very simple method called create async. All it does is takes a lambda, and all you do is return back your synchronous process image. What this does is it's underneath. It's like 900 lines of template goo that makes it. It's like just this 2 lines of code actually generates 800, 900 lines of template goo in the back, and it figures out, oh, this is the return type. This is what you mean. This is the iasync operation you need to create, and so on. And it returns an iasync operation. Now you've created a first-class Windows runtime async operation that can be used anywhere. So once you register it as a Windows runtime component by using what Hattie showed in the previous talk, you can now use it anywhere. You can share it with your colleagues. You can also share it with, ship it as a library for use from JavaScript, from C#, or from anywhere. So you have a lot of existing assets that are already synchronous. If you need to make them asynchronous, there's one simple call will make it async. I'd like to introduce you to Genevieve Fernandez. She's a senior developer on the PPL and the concert team. And she's going to show us a demo on how to do the create async.
Switch. Hi, everyone. My name is Genevieve, and I'm a dev on the PPL and concurrency runtime team. I've been on the team for about 5 years, and only in this release we started working on PPL tasks for asynchrony. So what I'm going to show you today is actually something that we shipped in our sample pack, first around the developer preview, and then we updated it again recently for beta. So this is one of the apps that uses, this is a hybrid app, which uses JavaScript and C++. And similar to what Harry showed you before, the C++ app is the one that does some heavy processing and exposes its functionality as an asynchronous operation that can be used from different languages. So let's take a quick look at this one. So my component here, so this is actually the sample pack. It has a whole bunch of other samples that also demonstrate PPL functionality. This is mostly around Metro, so they all are Metro apps. The image cartoonizer GUI is the one we're looking at today. And the image cartoonizer backend is the C++ component DLL. So pretty simple to define a component. You just have a ref class, which has a public method. In this case, my method, which is asynchronous, is get transform image async, and it returns an async action with progress. Now, how do you create one of these? So Rahul showed you how to create an async operation, and the way you do that is you have a lambda that returns a result, and the result of that lambda becomes a type of the async operation result. Now, in this case here, we don't return anything, which means we are going to create an action. There's no return result. But we do take a progress reporter as an option. Let me just increase the font size a bit. So that's how create async can tell what kind of operation or action to produce. If you return a result, you're an operation. If you take a progress reporter, you want progress reporting. So you're an action with progress or an operation with progress. And the way in which you would report progress is calling a simple report method on this progress inside this function that I'm not going to go into. It has a bunch of stuff that I didn't write. In any case, simply returning this function from inside create async will create one of these asynchronous types. Now, in this case, transform image does all the heavy lifting, and we want it to run asynchronously. But there are also cases where you might want to take a bunch of tasks and actually put them together in an event chain and return the final result. And you can do that as well. The thing to note there is that whatever you put inside create async, if you return a task out of it, all of that code executes when you call create async. It executes inline. The assumption there is that, well, your heavy lifting is being done in the task, so that's the asynchronous work. And the lambda of create async must run synchronously. So something to be careful about when you author async operations. You might make the mistake of doing something really time-consuming and then returning a task at the end and not knowing why your UI is frozen. In any case, let's go to the JavaScript front end. And here you have, I create a new image cartoonizer backend image transformer. And as simple as that, I can consume it from JavaScript. And note that JavaScript has made the get lowercase like it does for most of its, for all of its APIs. And the way to continue an operation in JavaScript is by using .then and supplying 3 different delegates. One of them is what will happen on success. Another one is an error handler, and the third one is a progress reporter. So whenever the component in C++ calls report on that progress element, the update progress function here will execute. So now let's see if we can run this. So I'm going to load an image. This transformation is cartoonization, and it also flips the image around. And you can see the progress bar is highlighted because of the progress reports that I'm getting. And then I have the image finally transformed. So this is one of the, I would say, 6 samples in our sample pack. If you haven't seen it yet, there's going to be a link to the pack in Rahul's slide deck. We encourage you to take a look at it and offer us feedback. Be active on the forums. We look at that quite closely. And that's about it. I'll hand it back to Rahul.
Thank you. All right, so with that demo, there's one last section I have, which is slightly advanced. And I promise I'm not going to show too much code. I've taken all the code and put it at the end of the deck. I'll make the slides available so you guys can, you actually need to sit down, look at it for 20 minutes, go away, come back, look at it for 20 minutes, go away, and come back, and then it'll all make sense eventually. But I'll talk about a specific concept that's, I think that's pretty important for us. So given that async is everywhere, nesting async just happens now. So this is a real example. So you do a get file async, and then on the continuation of the get file async, you end up saying open async, which is also async. I'm already on the other thread, but I don't have a choice. I have to call another asynchronous operation. In that continuation of the open async, I have to say load async, which is another async operation, and I have to say schedule this continuation in that. So now what I have is inside a continuation, I have another continuation, and I have another continuation. And if there's an error all the way in the middle, how do you make sense of this error? Like, where do you fail? What should you tell the user? What should happen to the continuation of the get file async.then if that had another .then that says go update the UI thread? So it becomes really, really blurry. You'll be writing a lot of try-catches. You'll be writing a lot of hacky code everywhere. So our developers, the genius developers, came up with this idea called task unwrapping and async unwrapping. So bear with me for a second. So what we do is you have get file async. Now, in the continuation of the get file async, you don't actually set up another async operation and do a .then there. Instead, what we tell you to do is return the async operation, right? Return the async operation from the .then, but put the .then outside of the scope and put it as a continuation of the get file async. Okay? So what we've done is instead of, I'll say it again. So what we've done is instead of putting the blue box .then as a continuation of the open async, we're asking you to return open async. Okay? So it returns an async operation, and we're saying put the .then as a continuation of the .then of get file async. All right, so what happens underneath in a nutshell is we actually package this. We recognize this, that you're returning an async operation. We put another task around it. We create another partial order for you, though you don't. Though it wasn't the case in the first thing, in the first diagram. So in the first diagram, the blue box had exactly one parent, and that was open async. Okay. On the right-hand side, the blue box actually has two parents. One is the open async. The second one is the green box, the continuation from get async. It is efficient. You don't lose any efficiency. There's no efficiency concerns here. But what you get is you now end up creating a ladder instead of a nest. And what can you do? Our task-based continuation will be able to catch the exception no matter where in the chain it happened. Okay? So I have code for this at the end of the deck in the backup section. I'm not going to go into it. It's Friday afternoon. But I'll make the slides available, as I said. But this is a pattern that we recommend. So what do you get? So essentially, don't try to read the code. Essentially, you go from the code on the left-hand side. Again, that's naive code, to nice compact code on the right-hand side, the right box. So that's what you get with async and task unwrapping. Okay? So just to recap, async keeps your applications responsive, so use it. PPL makes async simple and powerful, and we're working pretty hard to make it as part of the ISO standard, C++ standard. And we looked at how to do async. So we looked at how to build tasks, continuation graphs. We looked at how to do errors, cancellation. Then we looked at how we brought PPL to Metro. PPL task to Metro, and how that is the projection for async operations in Metro apps. We also showed you how to create your own async object and consume that from C#, JavaScript, and whatnot. And we looked at the async and task unwrapping as well. So thank you so much. Feel free to contact me. My email is rahul.patil@microsoft.com. Follow our blog posts, although it's a little bit more ampy right now. The C++ AMP blog posts dominate. They're V1, so they're putting out a lot of content. But you will see periodic updates from PPL as well. Download the sample pack. That's what Jenny showed you today. And feel free to ask a question in the MSDN forum. So thank you.